So here I wanted to give an overview with some good definitions, examples, pictures, and extensions as to what the different types of attractions we might be talking about here in Unit 3 with intermolecular forces. So intermolecular forces will often abbreviate as IMFs. It is not the same thing as a chemical bond. It is the attraction that holds one molecule to another molecule. So when we're talking about something like water, we're not thinking about the H to O to H that keeps that H2O together. We're thinking about how well is one H2O stuck to a separate H2O. And this is super important because these determine all of our physical properties. The ones that we use a lot are melting and boiling point, which relate to the state of matter. Sometimes we're asked about vapor pressure, which is that transition from a gas to a liquid, or occasionally a gas to a solid. And then surface tension also comes in for liquids, although we're not asked to describe that as much. So once again, we are not talking about a Lewis structure and whether we have a single, double, or triple bond. We are talking about after I have a complete Lewis structure, is that molecule attracted to another molecule of the same type or a different type? For intermolecular forces, it's totally fine to always use the phrase IMF. Sometimes you'll also see the phrase interparticle force. Both are correct, and we're talking about separate things that are not actually sharing electrons, but are attracted in some way due to their charge. The three main types of IMFs are hydrogen bonds, dipole-dipole attractions, and London dispersion forces, and we just need to know and use those terms a lot until we're comfortable with them. The three below the line here are intermolecular attractions that we would have if we had a mixture of two or more different types of compounds. So we see the definition here, and we'll hit the highlight of each type, but the type of IMF is based upon what is in the molecule. Is the molecule polar or nonpolar? Does the molecule have an ion or not? And does the molecule include a hydrogen atom which is bonded to a nitrogen, an oxygen, or a fluorine? So we're really looking deeper into a Lewis structure or a picture or a formula that is already done for us. So the London dispersion force, even though often we would describe this as the weakest in a one-to-one comparison, is probably the most important. Every single molecule that has electrons exhibits LDFs, and it is an attraction that nonpolar molecules have for other nonpolar molecules. Or maybe better said, it is the only attraction that nonpolar molecules have for one another. So when we say something's nonpolar, that means on average our electrons are distributed equally. But our electrons aren't always staying exactly in one place. They move and they wobble and they are random in their motion. And that random motion can cause at any moment one end to have a higher collection of electrons and the other end to have a lower collection of electrons, or distribution is a phrase we've used a lot. So we, at that moment, have more electrons here than there. We have a dipole. But that is a temporary dipole because the electrons are just going to keep moving and they're going to go back to balance out in a nonpolar molecule. But because for that moment we had a positive and a negative end, it can stick to anything else with another positive and another negative end. So when we have a polar molecule that starts to wobble its electrons next to another, nonpolar molecule wobbling its electrons next to another nonpolar molecule, we get a weak induced temporary dipole attraction that we call a London dispersion force. It is the attraction that nonpolar molecules have for one another because of the random motion of electrons. It's hard to show it in a still picture, so a lot of times we'll kind of see this as like a video or that wobble of where the electrons are going. Polar molecules have electrons that are randomly moving, so they can exhibit LDFs, but they also have a permanent dipole. They have an end that's negative and an end that's positive. That's why in Unit 2, it was so important that we could define things as polar or nonpolar based upon things like lone pairs and distributions of electrons. When something is polar, it's got that positive end, it's got that negative end, and that positive and negative is permanent, so it will stick to other positives and negatives. And that attraction can be a little bit stronger because it's a little bit larger and a little bit more permanent. There is a special category of intermolecular forces like the others, but it is so much stronger that it gets its own name, and it is super important in chemistry, but also beyond chemistry, in our medical and our biomedical applications. It's called hydrogen bonding, and it's still not a bond. Within water, there's an H bonded to an O. That's a covalent bond. But the fact that one water sticks to another water is called a hydrogen bond in the IMF category. It is not the same thing as a dipole, but it has some of the same characteristics. We have something with an unusually high charge, something with a super high electron density that attract and stick together. In a one-to-one comparison, it is the strongest of our IMFs. And here I say it's an especially strong version. It is like an especially strong version. And we won't have to kind of distinguish the difference there, other than it has to be the element H. And it has to be the element H because it's so small and it has so few electrons. But that H has to be bonded to one of our most electronegative elements, one of the ones that's going to pull the electrons from that H most strongly, an N, an O, or an F. So in that case, we have a very electronegative element and we have a very electropositive hydrogen. That very negative thing and that very positive thing stick together. But once again, it's important that that hydrogen is bonded to NO or F, but it's also attracted to a separate molecule, a separate N or F. So we can kind of think of the hydrogen as the cream in a hydrogen bond Oreo. It's got to have an N, an O, or an F on one side. Then we've got our hydrogen, and we've got to have the N, the O, or the F on the other side. So it is the most specific, and it must have those specific elements in those ways. The other types of attractions can't happen within an individual substance because we can't have a substance that's both ionic and polar. But if I put salt into water, salt is ionic, water is polar. So the phrase we use to describe why an ionic thing sticks to a polar thing is called an ion to dipole attraction. It's a very, very strong attraction because we're looking at very high charges, a full +1, a full +2, a full +3, or -1, 2, or 3 sticking to our molecules. So we get a nice strong attraction, which is what allows these to dissolve and stay dissolved. When we have an ion that has a charge, and even when we put it with something non-polar, it can make those electrons wobble in a specific way. It can pull electrons towards it if it's a cation, or push electrons again away from it if it's an anion. But really what we're recognizing is if I have something ionic with something non-polar, we have a specific phrase for the fact that there's a little bit of attraction between them. It is called an ion, because we have ionic, to induced dipole. And induced dipole is another phrase or another idea related to London dispersion forces. A temporary, weak polarity caused by that motion of electrons. The last type is something that sometimes we even overlook or we pretend isn't important. Polar things can attract to nonpolar things, and nonpolar things can attract to polar things. Because polar things have partial charges, they can cause the electrons within a nonpolar thing to wobble in a certain way. Because nonpolar things have electrons that are wobbling, they can have temporary and weak positives and negatives that stick to things with positive and negative charges. This attraction is generally not as strong as some of our others, like our hydrogen bonds or our dipole-dipole, but there is an attraction, and as we list our attractions here, if we come back, we are just stating what do we call it based upon which two things are sticking together. A polar with a polar, a nonpolar with a nonpolar, or some sort of combination of ions, polars, and nonpolars. Hydrogen bonding is the most exclusive, and hydrogen bonding is exclusive to not just H, but an H when it is bonded to an N, an O, or an F.